The last time we dealt with this, what kind of sequence are we dealing with here? Or series? So this was an application of our formula for arithmetic series, and we simplified it down to get that n squared, and we also saw it just by adding up a few terms and seeing that pattern. So what we're doing differently here is that we are going to now prove that this formula works. We already know it works, so what we're focusing on is how we're proving that it works. And not just for 1 or 2 or 3 odd numbers, but for any amount of odd numbers that we add up. Okay. So I'm going to do this in kind of 2 steps, and the first step is going to seem kind of silly. So I could start with the very simplest case, and I could say, well, if I just have one odd number, that's 1 over here, and the formula, our shortcut, says it should be 1 squared. Well, that's true. So it works when n equals 1. But now we don't want to continue in this fashion, because then we could say, well, okay, we'll prove it when n equals 2 and n equals 3. But then we're going to be here for an infinity amount of time. So that's not super efficient. We'd like a better way. Okay, but we've got it works for the simplest case. All right, so now I'm going to do something kind of strange. I'm going to say assume that we have proven it works all the way out to some amount of odd numbers, to like k odd numbers. And by it, I mean this shortcut. And I'll even call it that, because this gives us a way to easily add up n odd numbers without actually having to add them up. We just figure out how many there are and we square them. So it's kind of like a formula that gives us a shortcut for the sum. So let's say we've already established, we've just actually added them up to k of them. And so, to k, but if there are k odd numbers, I've done something wrong here. I'll figure out what it is.
K minus 1.
Okay, because that's what the number will actually look like. This is the kth term. Thank you. Okay, and what should the sum of those k odd numbers be? All right, let's pretend like we've already proven that that's true. We haven't, but let's pretend. So now what we're going to try to do is we're going to try to show that if we add one more number, this shortcut still works. So we're going to try to use what we already know to make it work for the next odd number. And so what this looks like with like a concrete example here is, let's say that I've added up 1 plus 3 plus 17, let's say. 17, how many odd numbers until we hit 17? 9. How do we figure out 9?
Plug it into 2n minus 1 equals 17.
Okay, so this is 18 minus 1. All right. So suppose we've already figured out that that equals 17 squared, because we actually added it up.
It's 81, actually.
Yep. Why?
It's 9 squared, so it's...
Oh, okay. That's what I need to... No. Uh-oh. I tend to get the eraser mixed up with the pen, so sorry in advance. Especially when I get 17 mixed up with 9. Many things. So we gaze at that. So we added up 9 odd numbers. We got 9 squared. And so this is saying now, what about k plus 1 odd numbers? So 1 plus 3 plus 5, all the way up to the kth one, and then plus one more. And then the k plus 1 odd number, we use the same formula to find it. So we take 2 times k plus 1 more, and minus 1. And what we would like to show is that our shortcut formula still works. So that would mean if we add up k plus 1 odd numbers, oh my. That's probably enough. Our shortcut formula says that should just be the square of k plus 1 terms. So in our example of here, where we went up to 17, this is like saying, nah, I want purple. So it's like saying we add on one more number, and we're trying to show, is this actually equal to one more number? We have 10 terms. Is it 10 squared? So, to do that, well, we could do this two ways. We could start again at 1 and do 1 plus 3 plus 5 plus 7 and all the way up until 19. Or we could say, well, we already figured out 1 to 17 added up is 9 squared plus 19, and that's 81 plus 19, and that in fact is 100, which is 10 squared, and that's what we wanted. So we're going to try to do the same thing here in our general case. But first take 15 seconds, turn to the person next to you, and see if you can explain why what we did is not just adding up the numbers from 1 to 19, 1 by 1 by 1 by 1. What did we do from here to here? Talk. And also, how did we know this was 9 squared? Explain to the person next to you.
It's easy, but not exactly, but I think I sort of get it. So we have two commands, one equals like 3 squared, right? So then it's logical we can like add another number, right? Because it is an n term, right? So we sort of have the second, right? 2, right? This is k plus 1, right? This is minus 1. Did you get how we can do that?
So the 9, how we recognize
I
that?
know, I'm just asking.
Okay. Were there any other questions that came up?
Okay. Yes.
So 7 set it to 2k minus 1.
Yeah.
And then you just solve it. So that's what 18 plus 2k. That's okay.
Yeah.
And I determine the k squared. Just 81.
Yes. One. And that proves. No, it proves. Yeah.
Alright. So now, I'm going to bring it back together here. So we showed that it worked when we go from 9 terms to 10 terms, but we haven't shown that it, like 10 to 11, 11 to 12. So now that's what we're trying to accomplish here. Because k stands for any amount of odd numbers, we're trying to add one more and show that it works. And it is our shortcut formula. So let's take our k plus 1 odd numbers here. Nope, not literally. Okay. And we notice, 5 lost his top. Okay. We notice that actually, just like we could replace 1 through 17 with 9 squared, that's sum, we can do the same thing here because we know, well, we assumed that it works. So we can just replace the first k terms of the sum with k squared. And that's what we're going to do here. Then we have the k plus 1 term, so the 19. All right, so now I'll just bring this together. We've got k squared plus, let's expand that to 2k plus 2 minus 1. You guys are getting a special show today. Sorry. I nailed it in A block. I know you think that I'm making that up, but really, ask somebody in A block. I did not fumble nearly so much. I guess I spent it all there. Okay, so k squared plus 2k plus 1, we're asking, is that the same thing as the square of k plus 1? Yeah. If we multiply this out, we'll get that. Or if we factor this perfect square, we'll get k plus 1, the whole thing squared. So, our shortcut formula works. Okay, now, of course you did. Do you guys know how I convince it to be less small? Or like how to get rid of this?
I like it.
We like it like this? Can you actually read it though?
Yeah.
Yeah? Can anybody not see it? Oh, to be young again, have eyes. That's nice. Okay. Well, working eyes. Yeah. They only work for so long. Very sad. So, we've proven it for every single amount of odd numbers that we want to add up. And here's why. We said that if we assume that we've shown it for one case, then we can prove that the next case also has to be true. Well, up here we proved it for n equals 1. We actually just checked that it worked manually. So we know 1 works. Okay. But now if we know that 1 works, now this says once you know that it works for one number, we know it works for 2 numbers. Okay, so now we know it's going to work for the sum of 2 odd numbers. Oh, but now, if we know it works for 2 numbers, this step says, now we also know it works for 3 numbers. And so it might take us a while, but eventually we could keep repeating this over and over and over. If we want to prove it works for 6,000 odd numbers, eventually we're going to get all the way to 6,000, because we'll prove that it works for 5,999 odd numbers. And our induction step says here that once it works for that guy, it works for the next one, for 6,000. So any number we choose here, it works, which means we've now proven this formula always works, no matter how many odd numbers we add. But we didn't have to do infinity number of calculations, we just had to use this one clever piece of logic. Pretty cool, huh? Okay, turn to the person next to you and see if you can explain that pretty cool piece of logic. How did we just prove that we can add up 6,000 odd numbers and get 6,000 squared?
So